In today's video, we will be looking at how different single-point mutations within a DNA strand can affect how and which amino acids are formed. Before examining these mutations, we must create a 5-amino acid protein from the sequence given. We are given this following sequence in which the template strand of DNA is read in a 3' to 5' direction, located on the bottom, and the coding strand read 5' to 3' on the top. However, this perspective only gives us a 4-amino acid protein, which is not what we need. We must flip the DNA sequence, giving us the following coding and template strands. Transcription occurs in the 3' to 5' direction, giving us the following 5' to 3' mRNA sequence. From this sequence, starting at the AUG start codon, we are able to form a 5-amino acid protein with methionine, valine, arginine, phenylalanine, and lysine. I like to think of these mutations like a frog hopping across lily pads, with each mutation affecting the frog's destination. The first mutation we will investigate is one in which transversion occurs, switching GTC to GTA in the coding strand. Since both of the resulting mRNA sequences code for the same amino acid, no protein change takes place, making this a silent mutation. The frog is happy because she has all 5 of her lily pads and can make it across the correct codon sequence. The second mutation results from the transversion of TTC to TTG in the coding strand. The amino acid coded for by the mRNA codon UUC was phenylalanine, while the mutated codon UUG now codes for leucine, making this a missense mutation. This mutation will give us a 5-amino acid protein, but the protein's function may be changed or inhibited due to the presence of a different amino acid. The frog is unhappy because even though her 5 lily pads are present, one is different and too far away for her to make it across the codon sequence. The third mutation we see is another example of a transversion of AAG to TAG in the coding strand. Unlike the other mutations, this mutation will not result in a 5-amino acid protein, as the mutated sequence of DNA transcribes to form UAG mRNA, which codes for a stop codon where we previously saw lysine. Because this mutation resulted in a premature termination of translation by changing a normal codon to a stop codon, it is a nonsense mutation. The frog is once again unhappy because she has to stop prematurely before making it to the normal stop codon. The final mutation we will investigate is a transition of TAA to CAA in the coding region. The result of this mutation is the stop codon UAA being changed to a functioning codon CAA, which codes for glutamine. Because the stop codon was replaced, a longer than normal protein will be generated, making this a read-through mutation. The frog is unhappy and tired as she now doesn't get to stop on her stop codon rock at all.